So welcome back, everyone. We're finally doing machine learning stuff, which is exciting. And let me just pull something up here. Okay, so we start with my famous announcements at the beginning of clarifying some things, and then we'll get into the core stuff again. So I wanted to clarify a couple things that came up, I guess, in Piazza or from office hours and other things I heard about. And 1 second. Okay. Yeah, so let's start with pointing out one thing. So we had this predictor, learner, business, and I just wanted to point something out. So one thing is that I'm going to just slightly change the convention of things we've been seeing, which is I'm going to say that the thing that the learner outputs is not just denoted by F. I'm going to just give it an F hat, okay? And this just is to be able to distinguish this, the thing it outputs is F hat. When we talk about general functions that are predictors and stuff, we're going to just use F. You'll see it throughout, but I'll point it out in a second. But the point is, just think of F hat as the thing that the learner actually outputs, and then F is just going to be any possible function later on. That's going to be kind of the notation. And this will allow us to more easily distinguish about what's the learner actually outputting. Okay. Just a notational thing. We could have just kept it as F, but we're going to change it to F hat. Okay. Other thing is there's this slight confusion, which is, so we have this data set, right? This is the data set. And you can think of it as having these n feature label pairs, right? And there's a learner, somehow it's going to take this data set and learn something called a predictor. And then it's going to output the predictor, right? This is what this F hat is. And the predictor better be able to predict something, let's say the price of a house for any house, right? Not only the houses in your data set, it better be able to predict it for any type of house. And give me any number of rooms, any age of a house, I better be able to predict that. And so in particular, this function F hat that you output, this X that it can take as input can be any X, right? It can be any type of feature. That's your goal, is to be able to predict things well for any possible feature input. Okay, so this thing that that we pass in as input is different than the data points. The data points is just data to learn from, and then at the end, your predictor can take as input anything. Okay. Some other confusions, which are very natural, is about these things called random variables, and then instances or outcomes from the random variable, and what we use for stuff. So that's the stuff after this bar here. Okay, and I wanted to hopefully clarify some things here. So we call this capital letter thing X a random variable. So we almost always use capital letters for random variables, and we'll say something is a random variable if it's in some set, which we'll call the outcome set. And it has a distribution P, which means we can talk about the probability of the random variable taking some outcomes. Okay. Then there's another thing we use sometimes, which is just a normal variable, which is little x. We'll just write something is in some set. This is the usual notation you've always seen. Nothing to do with probabilities. It's just some variables in a set. And we're usually going to call this thing just a single outcome, or an instance of the random variable, or a fixed value of the random variable, and all this. There's going to be this multiple names, but this is just a variable, and most of the time you're going to see from the context where it's clear, it's one thing is just some instance, or just it's just a number or just an outcome. And the other case, you really want to talk about probabilities and stuff, then we're going to use this random variable thing. And you might think okay, what's going on? This notation looks so similar, it's almost like how can I tell this is just the capital letter stuff? And the answer is sort of yes. It's going to be apparent from when we say things in the context of things. But the short story is that unfortunately this is the situation we have to deal with, unless we want to get into more details of what these random variables are, which are actually these special types of functions, and we're not going to go into any of this. So this is kind of the unfortunate situation you end up with in intro to probability courses, where random variables seem almost like normal variables, but then you talk about their probabilities and stuff. That's just how it's going to be. So some things, some actual useful things to note about this, what this implies, is that we can say what's the probability that a random variable is in some event. So it has a probability distribution that we can talk about. When we use these little x as just being some instance of it, we can't talk about this stuff. This is not valid. This has nothing to do with like probabilities. It doesn't have a probability distribution with it. It's just like a number, let's say. Similarly, you can talk about the expected value of a random variable because it has a probability distribution. And if you write this thing explicitly, it's like you need the density or the mass, and that requires it to be a random variable. Similarly, this is not valid. You can't write the expected value of like a variable. There's no distribution associated with it. And then similarly here, when I said you have functions of random variables, you call this a random variable, like x squared is a random variable, if x is a random variable. When we don't talk about random variables, these are just normal functions. There's nothing to do with randomness. It's just, this is x squared. And so this is going to be like an important distinction. It's going to come up like in this class probably, and I just wanted to mention it beforehand. And in particular, how we're going to see this is in the following way. We talked about the data set as being thought of as like n independent samples of feature label pairs. And we use this like D symbol for it, just normal like capital D. And so here it had a distribution, which is like the distribution of getting like these n, let's say like feature label pairs and stuff. And that was a random variable. But similarly, we're going to like have this other thing, which is this calligraphic D, which is going to be called like an instance of the data set or a fixed data set. So this you could think of as like a very specific n feature label pairs, nothing to do with randomness. And we're sometimes going to want to just talk about this. Like you just have some fixed data set. We're not going to talk about where it came from. We're not going to talk about the probability that you got or anything. It's just like some fixed set of feature label pairs, and then we'll do some math with it and everything. And this becomes like a very useful thing. You don't have to do any probabilities or anything with it. And then we're going to end up returning and talking about it as, okay, this thing's actually random and so on. So at the end of the day, there's going to be, I'm going to make it clear hopefully, but there's going to be a distinction between thinking of the learner as like a random variable and thinking of it as not a random variable when we pass in just the calligraphic D. And yeah, so this will be important because like the short story is that we're gonna think of it this way to begin with. Like I'm gonna explain today, and then we're gonna just consider it in this way as just like a normal function. And then we're gonna do a bunch of things with it as a normal function. And then like probably like 2 or 3 weeks from now, we're gonna return back, and I'll mention this as well. And we're gonna say, okay, this thing's actually random. And what does that mean for us and stuff like this? So I'm highlighting it now, I'll highlight it at the end again. We'll see, just wanted to point out all these things. So, oh yeah, there's a question about like, is all of this information in the posted notes? Yeah, this should be more or less like the course notes, the written up course notes in the PDF has a lot more detail about talking about things. All this information should be there, I think. If it's not, you can ask on Piazza or something and I can add it or I can have a look. And yeah, I guess like a more high level note is that the course notes are just essentially what I cover in class, but with like more detail and like actually written out sentences of what things mean and stuff. These are just like the math parts and I guess the main important things. So those are like maybe like more of the ground truth information that you should follow. Yeah. Okay, and other things is like these lecture notes, I've shared them online and I shared like a written version that has all of it written up, and then this version called like the live version that doesn't have stuff written up, so you can pick whichever one you want if you want to write it yourself or if you want to just annotate the written ones, it's up to you. Okay, so right now I'm going through the live version, so I'm going to write everything today in class. Okay, so we return to supervised learning. And the story was like, what we were trying to address is what exactly does learning mean? And in particular, what does learning well mean? Okay, so where did we leave? Okay, and let me address one thing is like, I wanted to point out that now that I said that the learner outputs not f hat, we just changed the symbol. So like this, the predictor that it outputs is called f hat. And this will be like to kind of distinguish from the fact that this, we use the f in here. So trying to distinguish between these two things. So f hat is an element of that set, but like it's a very specific one. It's the one we actually output. So it's just some way to distinguish this. So we'll usually use something like this. Okay, so cool. Hopefully this doesn't confuse things more than help, but let's see. Okay, so returning back to the story. So here's the like supervised learning setting, and then we talk about the objective. So just a reminder, the setting is you have a data set. And for now, we think of it as random. Okay, we have this random data set. It came from some distribution. And we can describe that distribution by saying that each one of these feature label pairs was sampled from this marginal distribution of feature label pairs. And they were all sampled independently, so we had n samples of it. Okay. And once again, these things were thought of as features. The x's are features, y's are labels. Okay. And for this course, we're always going to assume that these features or feature, like they're vectors, and so we're going to call them feature vectors. Okay. And then I gave some examples, which was like, in the house case, you can have like, let's say, a feature vector of dimension 3, maybe representing like number of rooms, number of floors, and the age. The y is the label, the price of the house. Okay. Maybe a slightly more exciting and like a real one from practice is this classification of images. And here you might represent the pixel values of an image, of like a 20 by 20 image. Like every single pixel value is one feature in your feature vector, and so you'd have 400 indices of your feature vector. And then your labels are like, what's in the picture? Is it a cat or a dog or a bird or something like this? Okay. And then I briefly mentioned that like features and labels aren't so clearly distinguished. It's kind of design choice. Like, what do you call a feature? What do you call a label? And usually the label is like the thing that you care about predicting and the thing that's hard to get information about. Like, it might be easy to get a lot of pictures from the internet, but it might be hard to get labels of, is that a picture of a cat or is that a stop sign in there and stuff like that. So that's the high level story there. And then we started writing the objective. And we said that like informally, the objective is thought like this. Like, we want to learn, which means we want to produce a learner. Hey. And this learner should be good, or sorry, it should output something like a predictor that's good. And what that means is that we want a learner such that the predictor it outputs, which now I rename to f hat. So it outputs f hat. We want this f hat to be good. And in particular, f hat is what the learner outputs. Okay, so it takes in data, it outputs a predictor, and we want this to be good. And now we started off on this journey of trying to describe what is a good predictor. So what is a good predictor? And here we're going to just talk about like a general predictor f maps things from x to y. Okay. And I wanted to make one other note, which is that for the next like 2-3 kind of things I write, I just want you to forget about this whole data set business. Like, we haven't learned anything yet. We're just talking about a predictor. Like, I don't know where it came from. We haven't produced, just like, imagine you have a predictor, you just want to talk about, is this a good predictor or not? Okay. So we'll talk about how to get it after in a second, but for now, forget about data sets or anything. So you have all you have is this function, and you just want to ask, like, is this a good function? Like, was I given a good predictor function or not? Okay, so then we started off on our journey of trying to understand what would it mean for this thing to be good. So in particular, we do an example first. So we have a predictor, and this predictor is going to take as input the number of rooms in a house, and it's going to output a price. Okay. So now here's the example. Suppose we're given the number of rooms, and I'm going to slightly change. So I've decided to slightly change the story. So we're going to rearrange a couple of things from before. So here's going to, and this is hopefully going to motivate things a little better. So suppose we're given like some number of rooms, and let's say those 2. Okay, like we're given some house, it has a number of rooms of 2, but we're not given the price, and say like the price of this house was like $300,000. Okay. So we're not given this, and then the question is like, what would a good predictor do? Okay, this is where we got to last time. And I gave this like thing of, oh, it should be like kind of approximately equal to y. Well, like, let's do the story a little bit differently. And let's say this, like, clearly the best thing would be if this thing was just equal to y, right? Like, in particular, if I plugged in 2 here, I want it to give you 300. Like, if that's the correct price, I want it to output the correct price. Like, this is naive. Like, naively, this is what I want. And we'll see why I'm saying naively in a second. Okay, like, what else could you want for it? I output the right price. Okay, so then I'm going to forget about this question I asked last time about measuring the quality, because it's kind of unclear why we would measure the quality of, like, what do you mean measure? Like, just predict the right thing. What is there to measure? So let me ask another question. So, like, what if you were given another house? Right? So, like, what if you were given another house? But this house, like, let's say that new house has a number of rooms equal to 2 as well. But for some reason, the price of this house was now something different. Let's say it was like 400. That's reasonable. Like, you have two houses, they both have two rooms in the house, but like this one sold for more. Okay, so now I ask you the question of like, are you so sure about your predictor? Like, so now, okay, what would a good FB? Okay. So like, should it output 400 now if it gets its input 2? Should it output 300? Should it do something else? Like, does anyone have a guess? Like, what do you think it should do? Sure. Okay, so we've seen like, yeah, I'll take that answer. So like maybe, so okay, here's an answer. So like maybe I've seen these two houses, right? I've seen two houses so far, these two rooms. Like I don't know what I'm gonna get. So maybe I do like f of 2 is equal to, I don't know, 400 plus 300 over 2. So maybe I do something like in the middle of the two, right? So maybe this is good. It's like somewhere in between, like it's close to one price and the other. Okay. So then comes the natural question again, which is like, what if I like got even more houses that I need to predict? What if we got even more houses? Okay. And the way we're going to do this is we're going to draw a graph and kind of like think about what would a good predictor be. So let's do this. Okay, so this y-axis is going to be like the price. We want to, like the price of houses we get. And this x-axis we'll think of as the number of rooms. So what we've been doing so far is we've been looking at the case where there's 2 rooms, right? And what we've seen is like some data points for 2 rooms. So maybe I put like, oh, that's not what I wanted. Maybe I put like this 350 or something around here. And so what have we seen so far? We've seen 2 data points, and I'll draw it like this, let's say. Seen this one and this one. That's like representing the 300 and the 400, right? But like, take in that what's happening is like we don't know what, like we're going to be given some house or maybe multiple houses, and we need to predict them all. We don't know which number of rooms we're given. We don't know the prices of all of them. So like we can just think about like technically we want to do well for anything we're given, but like let's just draw some more. So maybe I'm given another house and it's like this price. Maybe that's like 360. I'm given another house. It's like weirdly really cheap. Then I get more, and so on. Maybe I get like another weird outlier over here. I haven't described what an outlier is, but okay. I get some data. Maybe it looks like this. Okay, I get like some things. This is like what I kind of see for 2 houses. Then you can imagine I'm probably not only going to see 2-room houses, like I'm going to see more rooms. So let's do the 3-room houses. And maybe here I see something like this. I see like a bunch around this value, whatever that is, and then I get like some really expensive one, some cheaper one again. I don't know, something like this. And then let me just do one more. So maybe there's like a 4-room house version. There, maybe a trend you see is, once again, it's more expensive kind of on average here, and something like this. I don't know. Okay. So I've only drawn some of the houses you might get. Like in reality, you can get any possible one of these with some probability. Okay. And the question now becomes like, what should my predictor predict? Okay. And maybe this is actually not super obvious, and it's going to be a design choice. But like once again, okay, I'll just tell you like this average thing. What would it look like here? Like this kind of average thing. Like a natural guess would be maybe I predict something that's like the average of what I saw, and maybe I pick this as my value of the predictor here. This is the value of the predictor here, and then this is the value of the predictor here. And I would call this like my F, and I'd say maybe like F is good. Right, that like sort of intuitively makes sense. It's somehow like close to the other prices that I've seen. Maybe something like that is good. And maybe, let me give, like, maybe a bad one is like, imagine I saw this data point and I just stuck to it. And then for here, I like chose this for some reason. I chose to like exactly be just this one. And then here I chose this or something. So maybe I'd say like F is bad because, I don't know, it seems like it's far away from the actual prices I'm going to be seeing and something like this. Okay. So this highlights 2 things, which I'm going to talk about in 1 second, but let me just answer this question here, which says, maybe add a feature called location of the house, which can affect the price. Yeah, so this is a really good point. So, okay, so this is not going to be covered right now. It's going to be covered kind of later on, but it's getting to the point that if I add more features, like describing things about the house, I may be able to predict house prices better. So like in that case, maybe I can distinguish between these 2-room houses because like maybe one's closer to downtown than the other, and that's why it's more expensive. And in this way, like this plot is not going to be maybe so what I would call like spread out in this case. It's going to be like more concentrated because you have more information. We're not going to get into that detail for now because it's not that important right now, but like that's going to be something we come up later. So like basically, if you could gather more information about the house and it actually is useful information for predicting the thing you care about, that's always good. But we say like we have some fixed number of features, that's all we can have, and then see what we can do with that. So that's going to be like the main focus for now. Okay. And then someone said average between the more cluster data can predict a better price and also adding more features to it. Yeah. Okay. So these are all good answers. So this is kind of like the intuitive feeling we have for what should happen. And so now we kind of like do this more formally. Okay. So the first thing we notice is that like we don't know what's the new house we're going to get. And in particular, the way we would say this is that we notice that this x and this y that we're going to get, they're random. So we would say that these are random. They're random variables. Sometimes you just say they're random. So these things are random variables. They can, and in particular, what that kind of means is that they're random, which means they can potentially be any feature label pair. And what I mean potentially is like maybe there's some that there's just like no probability that you're ever going to get like a 1 million room house, okay? But some are like more likely, and that's what the probability describes about these things. And somehow this is like these. So we want to do well like across all these things we see, but somehow like proportional to how likely they are to be seen. And so the answer to this is like the way we solve this is exactly what we've seen so far, but like more precisely, the answer is we will care about f of like this predictor we have being good on average. And we'll make this more precise in 1 second, but this is like the first idea. Is like we don't know what x and y is going to be. So what we should do is we should be good on average. On the average x and y, we kind of not the average x and y, but like on average when there's different x's and y's we can see, but we'll see what I mean. But we should be good on average. Okay. And then there's one other thing that we should probably think about, which is like we said that like this blue points and stuff, they're somehow good because like intuitively maybe they're close to the data points we're seeing. And so more precisely what we ask is like how do we measure how close this f of x is to y? Okay, so how close is like our prediction to the price? Like in order to pick the one that's kind of the average, you need some way of like measuring what closeness is. Okay. Yeah. Yeah. So that's also like a valid thing you can do is ignore the outliers and like, well, yeah, you can calculate these things, and I think that's done sometimes stuff. We're not going to do that. We're just going to like naively, you have this data. The outliers are very unlikely. So like, since we're doing the average, the likelihood that like you get one of those is very small probability. And like, and when I say on average, I mean really the expected value. And we'll see that in a second. So those are going to be multiplied by a very small probability. So it's going to be very, very unlikely. So it should be kind of like, okay. But yeah, these are all good points. So, and the answer is, so we need some way to like measure how close these things are. And that measure is going to be what we call, so we use this thing called a loss function. And you will hear this a lot in machine learning. And that's, you might have seen this in your first assignment, this little L is usually what we use for loss functions. Okay, and this thing is a function from some price and some other price. And you think of this first input as like the prediction, and this as the true price. And it gives you some measure of closeness. So it maps to some number, some real number. Okay, like usually the larger this number means, the worse you are. Like you're farther away. Okay? Smaller it is, the closer you are. You have less loss. Okay. So this is going to be how we measure this stuff. And then the question becomes like, what do we choose as L? And this is like a big and important design choice in machine learning. There's like some very classic ones, which is the ones we're going to use. And then there's like all sorts of different choices for different cases, which mean maybe do better and stuff. And okay, so this is what I mean to communicate is that the choice of L, the loss function, depends on your problem. And we're going to consider two like very classic ways to separate the problems. They're going to be called regression and classification. And we're going to choose different loss functions because there's going to be a different notion of like closeness. And yeah, that's what we're going to do for this course. But you could choose different ones. This is exactly like where we make a design choice. Okay. And so now we go into, I'm going to just like go into one setting first, which is called this regression setting. So this is regression, and roughly speaking, a problem is called regression if like these labels y, element of the label set, if these things represent something with a notion of order. Okay, what does that mean? What that means is like, to be able to say that 350, for instance, is like kind of like close to 400 and 300 and like it's more close to those than let's say like 1000 was or something like that. There has to be some notion of like ordering between your numbers, you know, like 350 is pretty close to 351. It's further from 400 and so on. So there's, when you have numbers, there's usually a natural notion of like ordering. And this is the roughly what regression people usually talk about is like, usually what that means is that this set y, this like label set, is the real numbers or some interval. So this is usually what you'll hear about regression is that like you have some interval or like the real numbers is your set of labels and you're trying to predict these numbers. More formally, it actually is talking about the case where these labels represent something with a notion of order. Okay, this is going to be in contrast to classification. I'll just like foreshadow now, it will come in like a couple pages, in which case there, if you like need to predict cat, dog, elephant, zebra, there's no notion of like order for these in general. And there you're not going to be able to say like, oh, zebra is closer to cat than it is to dog, or things like this. Okay, so this is in contrast to usually using numbers like here. Okay, and someone's gonna, there's some things, is this similar to k-mean clustering? The answer is not really, because here we're actually trying to predict like the right labels. In this k-mean clustering, usually there's no labeling and stuff. You just want to find like groups of things, but maybe I don't know. We shouldn't get into that now. And then the other question is, how can we say whether the data we have is accurate and can give good predictions? Okay, so I just want to say for now, let's forget about the, like as I said, forget about the data set. We still haven't seen any, we don't have a data, so we're not learning anything yet. So far, we're just saying we have a predictor, and I want to do well if someone gives me a new house. And then all I did is like think about someone giving me multiple houses. How, like, what would that mean to do well? And that was just to like simulate the fact that you don't know what they're going to give you. And you want to do well on anything they give you, any x and y. So what you're going to say is like, I want to do well on the like on average. I don't know what they're going to give me for x and y, but whatever they give me, I want to do well like on average. No data sets yet. Like I'm just talking about predictors. Like what would a good predictor mean? We're going to talk about how to use the data set to get this good predictor coming up. Yeah, and there's another question. What the curly y, is that what you said? Yeah, so the question is like, what does this curly y represent? This represents the set of possible values the labels can take. So in this case, it would be like the set of all possible prices. So we could use R for that, let's say. It could take any number. There's like no chance it's going to take a negative number, but sure, we can still use that set to describe it. And so that's all it's saying. It's like, this is a set of your labels. Sometimes these labels, I think I mentioned, are called targets. And then like in the classification case, the possible labels are not going to be like numbers, unless you map numbers to like objects like cats and dogs, but usually there'll be things like cat, dog, elephant, whatever. Quite a big difference in terms of like how you can talk about the relationships. Okay, and here I give some examples to help you maybe understand. It's like why, like these are examples of like what the label set might be. So it's exactly what you're asking. So like they might be house prices like we've seen, but then there's like all sorts of other things. Like for instance, you could talk about predicting stock prices, or maybe predicting the energy consumption of some house or some factory. Or I'll give one more, which is like weather prediction. You're trying to predict maybe the temperature, right? So this is like to really point out that this is, I mean, you can almost frame any problem you want to predict something as like one of these, or it's going to, or the other one, which is classification. So yeah, and in these cases, like weather prediction, what are your features? Maybe like it's like information about, I don't know, like the winds and other things like this, and you want to use all this to predict the temperature. Okay. Cool. So now I tell you what the loss that we're actually going to use is. So we use, and here's two choices. So the first one is maybe the more natural one, which we're not going to often use. And that one is going to be, so okay, here I have a loss function. I'm going to take in as input the predictor, right? And I'm going to take in the label. And I need to compare them in some way. And a natural way is to just take their difference, right? How far are they apart? And what I don't want to do is I don't want, like, I just want a number that tells me how far apart. Like, I don't want negatives to mean anything. And so like a natural way to do this is I take the absolute value, right? And that would mean that like maybe the distance from here to here is the same as the distance from here to here. I don't want to have this like negative distance because that doesn't really mean anything to me. So this is like one natural choice. And what this is called is, this is sometimes called the absolute loss, or the absolute value. Okay. And the one we're actually going to use might feel a little less natural than the one we have just defined, but it's going to be very similar, which is, once again, we take the difference. Okay. And we want it to be positive, but instead of using an absolute value, what we do is we square it, because squaring a number always gives you a positive thing. And this is called the squared loss. Okay. And it turns out, okay, so like this or this, like these are the two common choices. And it turns out we're usually going to use the squared loss for this course, so we're usually going to use this one. And like we'll see it in a few like lectures when we talk about how do we optimize our learner to find a good like predictor. And it's going to turn out, maybe a little unsurprisingly, is that there we're going to need these derivatives and gradients and stuff that we sort of reviewed before. And if you take derivatives, it's going to be much easier to take derivatives of a squared function than it is of an absolute value. That's kind of the story. So mathematically, it's a lot easier to work with. So we usually will pick this. That's like one answer. There's definitely some other ways to answer this too. Okay. So far I've defined the measure, but I said I want to do good on average, right? Over like, I don't know what this XY is. I want to do, like, I want this measure to be small on average. And so here we go. We use this thing that we've learned before, right? Which is the expected value. So we're going to talk about the expected loss. Okay, so let me write that. So a good predictor F should have a small loss L on average. Or more formally, it's like we're going to use the word expectation and average quite interchangeably. Okay. So let me write it down. So what is this object going to look like? It's going to look as you might expect. It's going to look like the loss function with your predictor in there compared to your label, right? And let's just analyze this object. So we have a random feature. We have a random label. We have a function applied. Okay, so first of all, this thing is a function applied on a random feature. So that's still a random variable. And then we have another function applied to now a random variable and a random variable. And what we learned is that that's still a random variable. Okay, so this whole thing is just a random variable. Why? Because it's a function of other random variables. Very important to remember. So now something like this should make sense, which is that if I take the expected value of this object, it makes sense because it's a random variable. Okay, and this is how this is one of the most important objects in this course is this object, and in all of machine learning, you will see it. So you have this loss function which measures how close is a predictor to its labels. You don't know which labels and which features you're going to get. So what you want is for this measure to be small on average. Okay, that is kind of like the story. And to make this even slightly more formal, is that these things, x and y, once again, we still haven't talked about data set, but we're going to say that these things come from some distribution. And that distribution is going to be this distribution over x and y. So this is like this house and price thing is coming from, let's say, like randomly gathering it from some city. This would be the distribution would represent the probability of getting certain houses and prices in that city. And so you want to do good on average over the houses that you see in that city in predicting their prices. Okay. So we get to a very important, okay. Before I now more formally state the objective, right? Because that was kind of our goal, is to get back to the objective and state it formally. And we're basically there, which is formally we want to output an f, this predictor. We want our learner to output an f such that this object is small. That's what we're going to write in a second. But before I get there, it's just maybe we think about this with we try to unroll this expectation to kind of interpret what it's saying. So let's try that. So let's do an example, I guess, an example with the squared loss. So what I'm going to do is I'm going to actually plug in a loss into this expected value. And I'm going to unroll the expected value, like its definition, using what we've seen in probability. And then we're going to try to understand the object. Okay. So I take this thing. And I paste it here and make it smaller. And now I write it out. Okay, so first thing is that we have a loss, right? And I'm plugging in the squared loss, so let's plug that in. So I have the predictor. And remember, when you work inside the expectations, you have little variables. These are the outcomes. And here you subtract from the labels. Okay. And I'm using the squared loss, so I square this thing. And now I want to take the average of this thing over all possible, the expectation is kind of the average over all possible values of x and y. So how do I do this? Well, I integrate over all values of y, and I integrate over all values of x, and then I write dy dx. One thing, you got to remember to weight this. You have to you're going to weigh each one of these x and y's with their corresponding kind of probabilities. And in here, this means weighing them by their corresponding densities, their probability densities. So we have this probability density function of x and y. So you multiply it by this, and then you have dy dx. And I'm going to write this in one more form that we've seen before, which is going to make this potentially much more interpretable, which is, I'll write it like this. So I rewrite this x, this integral of y. But let me separate them out. Then I have the squared loss as before. And now I'm going to break this object, this multivariate density, into two things using the product rule. So the first one is the probability of y given x. I suppose I put these little things here. And the second one, and so I'm going to write dy here. And the second one is going to be the probability of x dx. Okay. And I've written it in this explicit way with the brackets and stuff. This is all fine. You can change the order of things like this to emphasize the way to interpret this. Okay. So we first think about the object inside the brackets. And how do we think about it? We think about this as a conditional, exactly in the way that conditional densities or probabilities should be thought of. It's fix an x first, right? So this inner thing has a fixed x. Okay, it's conditioned on some x. So we're going to forget about the outside parts. We have some x, which means we have some feature value, say 2, like we saw, the number of rooms is 2. So that's what this conditioning is. And then we say, okay, I would like to predict the correct value of y, which is the price, for that specific number of rooms, that specific feature, x, that's been fixed. And I want to do that well, right, on average, over all possible values of y. So this thing tells you kind of like the probability that you're going to get a certain y conditioned on the fact that you're at 2 rooms. And this thing tells you the corresponding kind of like distance you are away from these things. Okay. So clearly, like things like around the average value, this is going to be higher than, like this is going to be a higher thing that's going to give you a higher weighting. Farther away, there's going to be much less likely. So like, just like intuitively for this case, these outlier things would have this P of y given x, this density of y given x, to be much smaller. So they're going to be much less important. While things around here are going to have a much higher density, and those are going to be much more important to do well on. And that's kind of how this is be emphasized. And then all you do is that this outer part is then thought of as saying, okay, let's do the inner thing, but consider it for every possible value of x. Okay. So some interpretation, because oftentimes you just see this object, okay, sure, this is a random variable, but like, how do you think of it? This is like really the way you want to think of it. Okay, great. Now we write the objective again. And I'll write this and see if there's any questions. And so now this is what I'll put is almost formal. Like we almost have it exactly like mathematically, rigorously what we want. But not quite, and maybe I'll ask like what's missing in a second here. Okay, so it's pretty short. And I can take the here, let's make this even simpler. So we go back to this objective here. And I'm just going to copy it. And then change just some parts of it. Great. Okay, so the first line is fine, right? Like we still want to define a learner. This is the mathematically precise, like the learner takes in data set, outputs a function. The thing we really want to change is this line. What did it mean for the predictor to be good? Okay, so let's replace it with a new understanding. Such that what? Such that the expected loss is small. Oh, and maybe let me mention one thing before I do this. There's going to be some useful notation we use to describe this object. So instead of writing this expected value of this whole thing, we're going to use another symbol called capital L. And this is the expected loss of a predictor F. Okay, just some notation. This will be very helpful to not have to carry around this object around everywhere. Okay. So now we write this objective. Such that L of our outputted, like the actual predictor we output from the learner is small. Okay, that's all we've changed. Now we have a more precise definition of what it meant for our predictor to be good. And okay, so I will leave a little bit of a suspense because I'm not going to answer the question I'm going to ask right now until like maybe 15 minutes from now, which is like, like maybe two things. Is like is there any questions about this thing? Like, is there any confusion and stuff? And maybe the second interesting thing is like, what's potentially weird or wrong or missing, and why am I saying this is still not fully formal and stuff? And a slight hint is that like, at this point we're going to, okay, yeah, like the data set is important. This is kind of a story here. Yeah, so does anyone have any comments before we? Okay, you can say something up there. Yeah. Sure. More? Oh, the graph, okay.
On the graph, are they the points that the function would generate, or are these from the data set?
So yeah, so this thing right here is just trying to like simulate what this kind of expectation kind of represents in like a very like in a crude way, in the sense that like you can think of what this thing represents is it considers all possible, okay, so this is the expected value thing. It's considering like all possible values of y and x and then weighing them by their corresponding probabilities of happening. One way to think about the expectations is to just graph some samples from the distribution. And that's all I did, is I just like took some, like I'm sampling these x and y's from this, where is it? There's some distribution here. There's some probabilities of getting every x and y. All I'm doing here is just plotting some examples of things I might get. These are less likely things. These are clearly more likely. And this is trying to represent that in the expectation, we're considering literally every possible value you could get, and we're multiplying it by the corresponding kind of like density, like probability density of getting that point. And this like kind of represents that. Is like here you have like more points, it's like more dense, there's like, it's more likely to get those. These ones are less likely. So it's just like a sampled version of that expectation. We're going to get into it actually in the next set of notes, but like, yeah, so nothing to do with data sets yet. Like, forget about the data set. Like, we haven't gotten any data set. We just have a predictor, okay? And we're just asking, like, what would it mean for it to be good? And I'm saying, like, okay, like, imagine someone gave you, like, more data points than just a single one. Then it kind of, like, makes sense of what to talk about, what good means. But at the end, you're really, like, going to want it to be good. Like, you get anything and you want it to be good on that. The way you describe that is by using this expectation thing, which says you would actually be good on average for any x and y you get. Yeah. Okay, I'll answer this question. Yeah, so for right now, just like, this is why I really wanted to emphasize, forget about the data set stuff for now. We're gonna, like, clearly you can see that the data set can help us calculate this loss. That's what's gonna happen. And that's like, the story is gonna be really quite simple actually. Like, we're gonna use the data set to help us calculate this loss, but the thing we, like, before we have this data set or anything, the thing, like, we have to establish what do we care about? And what we care about is this loss value in expectation. So that means like over every possible x and y we get, multiplied by like this corresponding probability you're gonna get. Yes, so the story is you care about this expected value, but like we're gonna find out shortly that we also can't calculate this thing. Like, to calculate this, you would actually need to know the distribution. And we're never like given, like, I don't know what the distribution of house prices and their like number of rooms is in this city, right? And so, yeah, like the thing is like, this is the theoretical objective we care about. If we could calculate it, then we would just pick the function that makes this the smallest, and we're gonna see that. But the problem is we're not gonna be able to calculate it because we don't know this, and I'm kind of like jumping ahead. But like theoretically, this is the thing we want. This represents like on average how you would do over anything you see in the future. And yeah, so we're gonna use the data set to help with this. But for now, no data set, just like, this is the mathematical object we want to make small, to minimize. Okay, there's another question.
We don't know the distribution, then how would we integrate using like with the density function?
Yeah, so like this is, it's also jumping to the future. So like this is part of the answer is like, if you want to make this thing small, okay, like let's make this thing small. Well, calculate it. Well, good luck. You're not going to be able to calculate this thing because you're not going to know this density, or at least in this problem setting, you're not going to know it. So the answer is like, you're not going to be able to integrate this thing. But that's what you want. Like, you want to get the value of this, but you don't have it. And you can't calculate it. And that's where the data set's going to help us. It's going to help us do something called estimate this value. But yeah, like these are all good. Like these are obvious things that like one would think at this point. It's like, and yeah, it's good to ask this. Like, we're not going to be able to calculate this thing, and that's going to be one problem. And okay, yeah, we'll talk about how to do that. Okay, let me answer these ones online, and then I'll go there. So what is x and y here? I don't know where that was, but like x is the features, y is the labels, like always. It never changes. Someone says, sir, why did you write pxy in the loss law? And how is that equal to pyx dy? Yeah, so I made a little bit of a, like, they're asking probably about how did this become like something like this? Well, all I did is I took this object and rearranged some terms. So I did the product rule, which was p of y given x times p of x. That's just the product rule. We saw that from the last class. I'm not gonna, I guess, go over it, but that's just like a formula. There's some intuition, like it kind of makes sense, you know. And then here you would write dy dx, and then all I did in this line is I rearranged these objects. I just moved y and then put this next and stuff, just so the like intuition was more aligned, and that is fine because here we're only talking about the y, we're only integrating with respect to y, so I don't need this thing here at all. I can take it outside, and that's like an integration property. And the last thing is, can you explain the integral of the squared loss? And I hope I kind of explained it again, but that was the the story, you have a function, and then the expectation is just defined as the integral over all the possible outcomes. And these are the possible outcomes, x and y, for a multivariate random variable. This is in the, I guess, in the probability section as well. There's like this case of like, if x and y are continuous, then it looks like this. If they're discrete and continuous, then it looks different. And we're going to see in the classification case here, you're going to have a sum. That's all that's going to change. But there's like these different cases. But it should make sense, I hope. Okay, I think we can maybe, okay, we didn't really get to the bottom of my question, which is what's wrong with this thing and what's not formal. And we will just go along with the suspense and slightly skip over that for 10 minutes and then come back to it. Okay, so keep that in mind that I was saying this is not quite formal yet. But before we address this whole thing, because like, yeah, okay, before we address this whole thing, let's talk about this other thing I said, which is classification. So I wanted to like formulate this thing first, and now I just like, I could have talked about this classification thing like in between, but let's just talk about the classification version. And the only thing that changes here is we just, like the problems is a bit different in terms of what the labels mean, and then we change the loss for that, and then everything else is the same. So we have classification. And roughly speaking, like similar to how, okay, should I do this example? Let's do the example. Okay, we do the example, why not? So to save some time, I'm going to just copy the story, and we're going to do another plot. And then we'll talk about the definition. So, okay, I'll write the definition first. I think it's easier. So the definition is if y, like this random variable, y element of the label space represents something, as you might suspect, without order. Okay. Usually, this set of labels, like y, is like some finite set of objects. So let's see. And here we do some examples again, like very short ones before we do the longer one. And that's like, what's an example of a set of y that like wouldn't have some natural order to things? Well, maybe the set of the type of wines. And here think of the set of like actually containing like, let's say 5 different types of wines. There's no like real notion of this wine is closer to this wine than that, maybe, arguably, okay? And then there's like type of image. Right, so here the features are like the pixels of the image, and then you need to decide which picture is it, is a cat, dog, or whatever. Usually it's like type of something, okay? Like type of email, is it spam or not spam? These are classic classification examples. Or like in medical stuff, you might say type of disease. Okay, so it turns out that it's useful to treat these two things differently because they have different like intuitive understandings, and so we're going to design the laws in a different way as well. Okay, so now I do the actual example, the slightly longer version. Okay, so let's do a longer example, and we do the same format as before. But now we think of f as not a predictor for houses. We're going to take that it takes as input the amount of a chemical in a wine and outputs the type of wine. Okay, so the output here would be something like, we talked about this like Barolo or not Barolo. We're actually going to do I guess a more detailed version, which is like, let's imagine there's like 4 or 5 types of wine. So you'd output like wine type A, type 2, or type 3, or something like that. Okay, and yeah, the story. Okay, let's you know what the story here is. It's like you get some new amount of a chemical of a wine, then you don't know what the label is, and so on and so on. So let's just jump to the plot right away and forget about this like slow process of building it up. And so what I mean is like, suppose you got multiple wines, and then the question becomes, what would a good F be? Okay, so now here, like, the plot's a little bit different, so let's do the plot. So on the y-axis, there's no actual notion of ordering, so I'm going to write things on the y-axis, but you shouldn't think of one being closer than the other because they're closer on this axis. So what I mean by that is this is going to be like the type of wine. And let's say we had 4 types. So we had type A, type B, type C, type D. And here, using these like letters should make it even more arbitrary. Like you have no idea what's closer to in type or anything like that. Okay. Before we had price here, right? Now we have type of wine. What's the x-axis? Well, the x-axis is the amount of a chemical. So here we have just one feature. The reason I'm doing one feature is that because plotting it is much easier. If I did 2 features, then I'd need a 3-dimensional plot. Okay, and now you can like think of maybe here is 0 of the chemical, and then like, I don't know, here is like 900 of the chemical, and so on. So now let's plot these things. So this is how I'm going to plot it. So like this A, I'm going to say like, okay, like for A, maybe I see some like around here, I see a bunch at this level of chemical, I see a bunch of like this type of wine. And then maybe I still see a couple at this, but like this is, I don't know, some outliers here. And then for B, maybe it's like at this level of chemical, then it's B. Then I have like a bunch of wines, and it would be this B wine. And then maybe some over here. And then like maybe C is like over here for some reason. And then, I don't know, D is like somewhere over here. So what is this whole thing saying? It's saying like, okay, if I look at the amount of a chemical on this axis, right? I see that like if I don't have too much of the chemical, then it seems to be wine A. If I have more of it, then it seems to be like between A and B. Then it becomes more of B. Then maybe it becomes more wine D. And then it seems like if I have a lot of this chemical, then it seems to be wine C or something like that, right? So like your predictor should like output one of these like labels and stuff. And like maybe a good predictor, right? It needs to predict for every input, for every amount of a chemical, it needs to predict some type of wine. So it's one of these 4 things. So the way you draw this is maybe it would be something like this. Maybe it'd be like here, and then you'd have this dramatic jump. That's not what I wanted. You'd be here, and then you jump to here, and then maybe you predict this wine here, and then you jump to here, and then you predict this wine, and then maybe you jump down, and then you predict this wine for the rest of the time. Something like that. So maybe this is like what F good means. So there's this, like it's these discrete type of things, and here you really, like there's no notion of closeness. You don't like, you either predicted right or wrong. And so like if you look at this and you try to interpret that there's some like notion of closeness in this y-axis and stuff, maybe you'd naively be like, okay, like I just predict like something on average, you know, something like this. And then obviously that kind of sucks, but like visually maybe you're like, okay, I kind of chose the average thing similar to like a regression. And so then this would be F is bad. Okay. They're just trying to emphasize that like, yeah, like taking an average or something of like you really want to predict the right thing. You're either right or wrong. Like you don't like, you're not close here. You're just wrong. You chose the wrong thing. And so our loss function here is going to be different. Okay. So now we do the loss function. So for L, we use this. And as the name might like tell you, so like, okay, so this is the function. Oh, right. You have a loss function. This thing takes in as input a predictor and a label, and it needs to give you some measurement of if it's correct or not. Okay, so when do you have zero loss? Well, you have zero loss if, as you might expect, if f of x is just equal to y. And so here this actually makes sense to use this kind of measurement. You're either right or you're wrong. Like for some amount of this chemical, it's one of these things. Okay, sometimes it's the other, but like it turns out you can't guess that one. You want to guess the one that's like right most of the time, because there's no notion of being close. You don't want to guess like some other line in the middle or something. And then you're going to get a loss of 1. You're going to get a loss of 1 otherwise, which means they're not equal. And this thing has a name as well. And this thing is called the 0, 1 loss. As the name says, it makes sense. You either get 0 or 1, 0 when you're right, 1 when you're wrong. Okay, so that's all there is to, okay. That's the story, and then you can write, you still care about the expected loss, you can write out that integral is going to have a, okay, maybe we write out the integral, because perhaps it's useful. So now we do the example of what is L of f if we use 0, 1 loss. Yeah, I think this is probably quite useful. You'll see this probably at least a couple times, and this way I can at least do it in the class. So we write the expectation explicitly again. So what's L of f? Well, L of f is the expected loss of our predictor compared to the label. And notice, just like I want to point out here, these are random variables, so that this thing is a random variable, and I can take the expected value of a random variable. Now, this is equal to just like a computation, and here there's no random variables, it's just like instances, and you're just doing this integral calculation. And so here, I'll write it out similar to before first. So you have this integral over x. Okay, x is always, in our case, feature vectors. It's always going to be like something in the real numbers. So we can always take this integral. In this case, it's just one real number. I'm sorry, it's like just in R, like it was just the number of a chemical. Then we're going to have a sum here now. And the reason we have a sum is because y is over this like finite set. So here you write little y element of y. And this would be this like this calligraphic y is just equal to wine A, B, C, or D. Right? These are types of wine. Okay. And now what do I do is I plug in the loss function. And I'm going to just write the loss function explicitly because I don't like plugging it in this piecewise thing is a little bit annoying, and I don't want to introduce new notation quite yet. And we will, there's a more compact way to write this, but I just want to mention, we're going to spend a lot of like the next like maybe 5 weeks just on regression, and we'll come back to classification. So I don't want to like overload notation with this classification stuff for now. And then you just have, as before, P of xy dx only, because you're only, the integral is only for x. Okay, this is all I really want to say is like here you have a sum now before you had the thing. And in particular, you might remember sort of briefly, like here, this is not a PMF or a PDF now because you have discrete and continuous random variables. And so like what you would actually do is you would once again use the product rule. I can make it a little more explicit by putting the brackets here, and you would have something like this. And these should be little. Okay, it's like same story, except inside now you have a sum. This is, we're going to come back to this in a lot more detail in like 5 weeks or something. So for now, let's not, let's not worry too much about it. But you can write it out, it's here. And yeah, someone said, can I scroll up to the wine example description? Sure. So this is the wine example description. And yeah, the story is you can, like, you either get the right wine or you don't. And I can take a question, I guess, in the meantime. Can you, so I'm confused. What do you, like, the 0-1 loss, like, you're either right or you're wrong. Like, you can't get close to being right, is like what it's trying to emphasize. Is like, you can't pick, like, if you're predicting, like, let's say cat, dogs, giraffes, zebras, like, picking a zebra is no closer to a cat, if it's actually a cat, than picking a dog or something, is the point. It's just trying to emphasize. But in the regression case, right, picking a number, like if the correct price was like 400 or something, then picking a price of 350 is closer to 400 than picking, let's say, a price of 1 million. So like the squared thing would be way bigger for 1 million times 350 than it would be for 1 million times 400, or sorry, 400 times 350. But yeah, okay. For the sake of time, I do want to, there's only a couple more things to say, and I think we can cover them all. So let's just come back to this objective. And let's answer this question that I was saying before of what's so informal about this, or what's missing. And so now we finally return. Yeah, I'm just going to answer it for the sake of time. But like now we're finally going to return to the data set. And we're going to look at one thing, which is that I said, okay, we have a learner, fine. We want this to be small, fine. That all makes sense. But here's a problem. Okay, I just read it. And the problem is the following. The data set is random. It's a random variable. Okay, so you might be confused what that implies. Okay, let me put it another way. So that means it can potentially be any data set. There's, of course, different data sets are more probable than others, but it can be any data set. Right? And what does that mean? That means if D changes, like the actual data set we get changes, right? Then what happens? Well, then most likely the predictor you're going to pick, F, also changes. And this is sort of like the problem we saw before. Like you get a house, okay, you predicted the right house. Oh, but like you don't know what house you're going to get. Like you don't know what price you're going to get. You're going to get, so similar for this, like we need to design a learner, but we don't know what data we're going to get. So we design like a good learning algorithm. And then someone goes and brings us this data set of houses. We're going to use this data set of like this giant data set of houses to predict the right price of some new house. But what if they give us a totally different data set? Like then we need to do well as well. And what if they give us a different? So we got to do well on like anything. Like imagine they come to us with a bunch of houses that have a large amount of rooms, and then there's like we need to predict we need to predict the prices correctly for all possible houses in the future, even ones with small numbers of rooms. Or imagine they come to us with a data set only having like houses with 2 rooms for some weird reason, like they got like that's how their random collection happened. And then what do we need to do? We still need to output a predictor that predicts prices of houses well that have like 10 rooms and 15 rooms and all this stuff. And so, okay, this becomes a problem. So if D changes, this thing also changes. And like, how are we going to describe that we want to do well for any D? Okay. So there's one naive way, like you might think, okay, like and I'm just going to say this kind of like in passing, which is like, can this thing be good for all possible values? Okay, for all values of D. And this means like for all values, like the data set could be. And it turns out that the answer is no. Like if you try to do well on one data set, that implicitly means like if you try to do, like if you're going to do well on the data set that you see a lot of expensive houses, then that means that like you're going to necessarily do worse on the case where you see less expensive houses and stuff. So, and I'm not going to get into too much detail of this, but like the answer is no, you can't. And the story is story is that there is a trade-off. Okay, and we'll talk a lot about this in maybe like 3 weeks. And what that means is like if okay, I'm not even gonna say what that means. Okay, all that to be said is like you somehow want to do well on like this data set. You don't know what it's going to be, so guess what the answer is going to be? The answer is going to be you want to do well on average. Okay, so you don't know what the data set is, but like you're going to get different kind of data sets. So like you want to do good on average over the data sets you might get. So here's the answer. Instead, we will care about A of D equaling to F hat being good on average, or an expectation is the actual like correct thing. Over what? Over data sets. So this is different than what we had before, which was over the feature label pairs that we're going to see kind of in the future. And so now we can finally write the object. Okay, so let me write that object. So what that object like really means is we had this thing, but F hat was random. It changes with the data set. So more importantly, what we would write is we'd write in here, and what was F hat? It was the output of the learner for a specific, like for the data set. And now, okay, this thing should kind of make sense. So I have a random variable, which is the data set. My learner takes that as input. It outputs a predictor. But since it took in a random variable, it itself is random. Then what do? I apply some function to it. Okay, it's this complicated expected loss function to it, but fine, I can still do that. That's still a function. What do I get? I get something random. Okay. And finally, what do? You take the expected value of this. And this thing is like a complicated looking expected value. We're not going to look at this thing until like 5 weeks from now or something. But okay, this is the thing we're actually going to care about, which is like we want to do good on average across the data sets. And then what that means to do good for like any one of those data sets that we would get is that we want the expected loss of it to be small on new feature label pairs we get. And so we're finally in place to write this thing formally. Okay, we still have a couple minutes to finish this. And that story looks as follows. So we replace actually these two lines here now, because like this is a random thing. So we need to talk about like what does it mean to do well for this random thing? Well, we erase all of this and we say now, okay, we can erase. Yeah. And we say instead we want such that the expected value of what the expected loss of our random predictor is small. Okay, so this is the actual formal objector now. Okay, so this is kind of the actual true objective that you care about in machine learning. And how are we going to like study this object? This thing looks confusing, and there's two parts to it. It's like this thing and the outer expectation, and we're going to study it in parts. And so I finished with like two sentences, I suppose, which is like, so this is what's going to happen is first, we will assume, and here comes an important part that I mentioned at the very beginning of class, which is like, first we'll assume we have a fixed data set. So there's no randomness to this data set. It's been given to us. And we're just going to study, like, if I just had these like n feature label pairs, what would I do with it? And so we're going to say D is equal to like this specific instance of the data set, calligraphic D. And this calligraphic D is not random. And we'll talk more about this. Okay. And then the reason to do this is that then we'll see how to define this learner for this non-random thing. So now we'll just have this like tuple of feature label pairs, which outputs F hat, such that, well, such that this expected loss of this thing it outputs is small. So this is going to be really the story of, I guess, oh, that's a nice rectangle. For a large part of the next section. And understanding this is like a really important, I guess, like maybe the most important part of the course. And then after we'll deal about this random data set. So I can end there. The next class I'll start with explaining very briefly the approach and then going over the parts. But yeah, so that's going to be our goal. Find this predictor.